So let's do a few practice exam problems to practice our skills of not only Lewis dot structures, but being able to determine what the hybridization is of the central atom in these molecules. Specifically, what hybrid orbitals are used by the central atom to determine something about the molecule's geometry. So we've got 5 examples here. We're going to do, get my little pointer here, we're going to do 3 in this video, and then we'll do 2 in lecture together, probably more than that, but we're going to do, in this little video, we're going to do XEF4, BR3, and SO2. So let's start with the xenon fluoride. I want to know what the central atom hybridization is. It means I got to do the Lewis dot structure. Determine what the central atom is. So number of valence electrons, which hopefully you should be able to do in your head, but number of valence electrons, xenon is in group 8, so that's 8. Fluorine is in group 7, multiply that by 4. So we should have a total of 36 valence electrons for that molecule. Xenon is by far the least electronegative, so xenon is going to be our central atom. I'm going to scatter my fluorines around it somewhat neatly. After I am done scattering my fluorines around, I'm going to start distributing my electrons, single bonds first from the central to the outer atom. 2, 4, 6, 8. I've used 8 of my 36 valence electrons. Next step, octets on the outer atoms. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I have used 32 of my 36 valence electrons. So I've got 4 more electrons. Anytime you have extra electrons after doing the octets on all atoms, always go on the central atom. So those remaining 4 electrons will be as lone pairs on the central atom. And so that's our Lewis dot structure for this molecule, and we're going to use it to say that, okay, I see that my xenon, which is my central atom, its Vesper notation is AX4E2, but more important, which is important, but more importantly, we need to determine the number of electron domains on that central atom, because that will help us determine the hybridization of that central atom. My central atom has 4 plus 2 or 6 electron domains, so it needs to have 6 hybrid orbitals, and the address or the hybridization must be sp3d2, because then that gives me a total of 1 plus 3, 4, 5, 6 hybrid orbitals. I'm going to mix 1s, 3p, and 2ds to give me 6 hybrid orbitals. So the hybrid orbitals used by that central atom in Xe have an sp3d2 hybridization. You could have also gotten that information if you're still memorizing. You could have also gotten that information from the previous chart that I introduced in the previous video. Let's do Br3, that anion. So Lewis dot structure again. Each bromine is 7, multiply by 3, but then I have to add 1 since it's a -1 charge. So I should have 22 valence electrons for that species. All of my atoms are the same, so it doesn't really matter which one I put in the center. They're all going to be bromines. I'll just consider one of them as like my central atom. So I'm doing my little sketch here. So I have my central bromine, single bonds first, 2, 4. I've used 4 of my 22 valence electrons. Octets on the outer atoms. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've used 16 of my 22 valence electrons. So I've got 6 more electrons, 3 lone pairs that are going to be placed on that central bromine. 18, 19, 20, 21, 22. I've now used all 22 of my 22 valence electrons. I need to put that in brackets with the negative charge since it's an anion. I see that my central bromine, its Vesper notation, AX2E3. E3. So that central atom, that central bromine, has 5 electron domains. So I need to have 5 atomic orbitals hybridized to give me 5 hybrid orbitals. So those orbitals, I'm going to have an S, 3 P's, and a D. So the hybridization on that central bromine is sp3d. Those are the hybrid orbitals that are used in the structure for that central bromine. 2 of them are used as bonds, to form covalent bonds between bromines. The other 3 are involved in holding those 3 lone pairs. Last but not least, let's do sulfur dioxide. Let's do sulfur dioxide. So number of valence electrons, oxygen group 6 multiplied by 2. Sulfur is also in group 2, or also in group 6. So I've got 18 valence electrons. Sulfur is my central atom. It's the least electronegative. Scatter my outer atoms. Do my single bonds. 2, 4. Octets. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Those 2 remaining electrons will be a lone pair on the sulfur atom. But hopefully you see now that, well, that sulfur, while the oxygens are happy, the sulfur is not happy. So I need to get my eraser and take one of those lone pairs and make it into a double bond. I could have a double bond between that oxygen and the sulfur. I could also, just to be complete here, do a resonance structure where I have the double bond be on the other oxygen. And so those would be the resonance structures for SO2. And actually, regardless of which resonance structure you look at to determine the central atom hybridization, you look at the central atom, and I see that, AX2E for that central atom hybridization, or central atom Vesper notation. So I've got 3 electron domains. So I need to have 3. I need to have 3 hybrid orbitals available, and I get that by taking 1 S and 2 P's to give me sp2. So my central atom in both of these Lewis dot structures is sp2 hybridized. So we'll do these other 2 examples in lecture, but you should feel comfortable being able to obviously give Lewis dot structures and say something not only about the geometry, like what we did in the previous chapter, but also what the central atom hybridization is. In the next video, we're going to start to talk about how are double bonds formed? Where are the electrons for a double bond? Where are they located? We will talk about that in the next video.